Okay, pre-calc students, we are still taking day 5 notes, but now we're talking about average rate of change problems. And the key to average rate of change is that it is only the slope. So when you see average rate of change, just think right away slope. Remember your slope formula is y2 minus y1 over x2 minus x1. So on this parabola, there is not a constant rate of change. The rate of change is changing throughout the parabola. You can see at the beginning, the graph is very steep. It becomes less steep and even less steep until it changes and it becomes negative. The slope becomes negative but even more steep, and then negative even more steep. So if we look at points on the line, for example, -3, -5 to -2, 0, we can use those points to find the average rate of change. So what we're going to do is subtract 0 minus -5 is 0 plus 5. And we're going to divide that by -2 minus -3, so -2 plus 3. I get 5 over 1, which is 5. Alright, at this point you should pause the video and find the rest of these slopes, and then you can compare your answers with mine. Okay, my answers are 3, 1, -1, -3, and -5. On the next page, we're also finding average rate of change, but the intervals just look a little different. So on this page, we're still finding the average rate of change, but the intervals are both listing x values. So you need to take those x values and turn them into points. The first one is the interval -2 to -1. So -2 to -1. If I look at the point where x is -2, I can see that the y value is also -2. So that is going to be the point -2, -2. And then if I look where the x is -1, that point is -1, -1. So these are the points I'm using to find the slope. And I'm going to subtract -1 minus -2. -1 minus -2, I get 1 over 1, so my slope is 1. That's my average rate of change. In B, you may have a typo. My paper said -2.8, but it should have been -2.7. So I'm going to find the average rate of change on the interval -2.7. And -2 still has a y value of -2, so that's the same point. But now I'm going to the point where the x value is 7, and I can see here that my y value is 1, so that would be 7, 1. Find the slope. I have 1 plus 2 over 7 plus 2. So I have 3 over 9, which is 1/3. Alright, looking ahead, you can see I've already solved the next problem, so you should probably try to solve that one without looking and check your work against mine. And if you haven't paused the video yet, you may want to pause it again before you look ahead to the next one. Alright, on the last graph, we're finding 3 different rates of change. And the first 2 are very straightforward, but in the third one, the interval is 1 to 3. So I can see that my y value is somewhere between -1 and 0, but I can't tell exactly what it is. So when that happens, what you can do is you can find f of 1 by plugging 1 into the function. It looks like a lot of work, but here's what happens. 1 minus 1 is 0. And 0 times all of this is going to make this whole product here 0. So this is all 0. I get 0 minus 0.5, which is just 0.5. And when I plug 3 in, 3 minus 3 is 0. And 0 times all of this gives me a product of 0 as well. So I get 0 minus 0.5 equals, they are both actually -0.5. So my 2 points will be 1, -0.5, and 3, -0.5. So when I find my slope, -0.5 minus -0.5, 3 minus 1, I get 0 over 2. So my slope here, my average rate of change is 0. Alright, we're going to move on and do our even and odd notes. If your teacher hasn't given you even or odd notes, you can just stop the video here. Alright, graphs can be described as symmetric to the x-axis, to the y-axis, to the origin, or it could have no symmetry at all. If a graph is symmetric to the y-axis, for every point x, y on the graph, there will be another point on the graph. So think about your parabola as an example. On your parent function, you have the point 2, 4, and because this graph is symmetric to the y-axis, you also have a point over here at negative 2, 4. So anytime x, y is on the graph, if it's symmetric to the y-axis, you will also have negative x, y on the graph. So if I give you one point, you can tell me another point on the graph just by using that symmetry. Just take the opposite of the x. You will tell me, in this case, that negative 2, negative 3 is also on the graph. Positive 1, positive 2 is on the graph. And negative 4, negative 2 is on the graph. If your graph is symmetric to the x-axis, it's actually not going to be a function because it doesn't pass the vertical line test. But if you were to have a point on this graph, x comma y, then reflecting it across the x-axis, you would see you have the same x value, but you have the opposite of the y value. So if xy is on the graph, then the point x negative y is also on the graph. So to find the reflection, you just need to take the opposite of the y value. So the first one becomes 2, 3. The next one becomes negative 1, negative 2. And the last one is 4, positive 2. If a graph is symmetric to the origin, it would look something like this. Here's one piece of my graph. Imagine it flipping across the x-axis and it would be down here, and then imagine it flipping it again across the y-axis and you would have this piece here. So y equals x cubed is an example of a graph that is symmetric to the origin. If I have a point on this graph, for example, if I have the point 2, 8, I will have another point down here at negative 2, negative 8. So if a graph is symmetric with respect to the origin, for every point x, y on the graph, the point negative x, negative y is also on the graph. So take the opposite of the x and the y. So in the first case, our new point is negative 2, 3. In the second point, our new point is 1, negative 2. And in the third case, our new point is negative 4, positive 2. Let's see, opposite, 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 opposite. It works. Okay, so graphs with these symmetries have special names. If a graph is symmetric to the y-axis, it is even. And if a graph is symmetric to the origin, it is odd. But sometimes we're not looking at the graph. Sometimes we're looking at an equation. So we have these second rules. A function is even if you can substitute negative x for the x and get the same function, f of x. And a function is odd if you substitute negative x for the x and you get the opposite of f of x. And if the function is neither the same nor the opposite, then we would say that it is neither even nor odd. So looking at these examples, we are going to substitute negative x for the x and see what we get. So when I substitute negative x, I get 2 times negative x plus 1, which is negative 2x plus 1. So I can see that's not exactly the same as my original function. The x term is opposite, but the 1 is the same. So it's neither opposite nor the same. So I would say that this is neither even nor odd. In the next example, I substitute negative x. And when I square a negative number, it turns positive. So I have x squared plus 4, which is exactly the same thing I started with. And that makes this function even. Okay, one more example. Substitute negative x for the x. When I cube a negative number, it stays negative because that's 3 negatives. Negative times negative times negative, it is negative. So I have negative x to the third minus x. I have the opposite of the first term and the opposite of the second term, so this makes this an odd function. And that's the end of your notes. You should start your homework assignment now.